All right, here we go. Excuse me. We're going to start on our actual notes for parameterization of plane curves. We're going to develop a way to think about curves that's a little different. Again, if you watched my little introduction video, maybe you have like a little bit better of an idea here, but we're going to basically, trace out a path, but we're going to keep the x and y basically independent of each other so that they don't have much of an effect on each other. Instead, they are both just functions of another variable we're going to call t. And typically it's t because usually this is done for time, where t is time and it tells you how much it moves horizontally versus how much it moves vertically. So for example, if I had a building I was standing on and I threw a rock off it and it went and it would do some sort of path like that, it would be a parabola. Well, at any point that you look on there, you pick it, and you have moved some amount in x as a function of how much time has gone by, and you have some sort of displacement in y also as a function of time. And they're going to be basically independent of each other. If you've taken physics, that's one of the things you learn. And we can do it like that. And really we can do it for any point on there. You could pick this point, and you'd have an x and a y, and you could have an x and a y could be, or I'm sorry, an x and then a y like that would be, getting you down here. And you'd have all these things, and each one of those things, the x's would basically start right here, and they'd go and expand out and just get longer and longer and longer until they reached this point, and the y's would get taller. They would go up, 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 and then they'd start pointing down, 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 not like that. So we'd have a separate function for each one of them to kind of describe this motion. So parametric equations, our definition, if x and y are given as functions, then we can have x as a function of time and y as another function of time, like that. And then we can put these together over an open interval I of t values, where our coordinates that are mapped up, or the vectors, the position vectors that are mapped out, if you watched my other video, is the x, y's. The x ones are the function of time f, and the y ones are the function of time g. And they're defined by these equations, and it's called a parametric curve. And there are advantages to doing this, as you'll see as we move further into this motion. So important ideas. The variable t typically represents time, as I've stated, so there is a motion to the curves. And we typically think of the curve as the motion of a particle over time, and parameterizations are not unique, which you could have seen in the last video if you had watched that little introduction I did. They are absolutely not unique. There's essentially an infinite number of ways to parameterize a curve. So let's take a look at an example here. This way is going to be a little different than what I did in the introduction. This is going to be more just we have the parameterization and let's figure out what it is. So sketch the curve defined by the parametric equations, then identify the particle's path by finding the Cartesian equation for it. So first, we need to figure out what the basic path is, and we can do this simply by doing a table where we can look at t equals 0, 1, 2, 3, so on and so forth, and we can say x is equal to the sine of pi t over 2, and then y is going to just equal t. So doing the y's is going to be pretty simple. They're just going to mirror over 1, 2, 3. And then for the x values, we have to actually plug these in. So the first one's going to be x equals sine of 0, because we plug in 0 for t, it all becomes 0. And the sine of 0 is 0. The next one is x equals the sine of 1, which is just going to be pi over 2, which is going to just be 1. And then x equals sine of 2 pi over 2, and that's just going to equal then 0 again. And then x equals sine of 3 pi over 2, and that's going to equal -1 for us, and then 4 pi over 2, and so on and so forth. And you can keep going that way and keep going that way. And we can actually figure out what our xy coordinates are that are being mapped out just by combining these together. So here it was 0 for x, 0 for y. Then it was 1 for x, 1 for y. So far, they're just mirroring into each other. But then we have 0 for x and 2 for y. And then we have -1 for x and 3 for y. And you could keep going on just like that to kind of see what is happening. And what you might notice is, as we're going along these points, we started here at t is 0, because again, we were bound for t to be greater than 0, but less than 6, so you could go all the way out to 6. But essentially, what's happening is we're going 0, and then we're going at t equals 1, we've got 1, 1, and then at t equals 2, so this is t equals 0, this is t equals 1. T equals 2 has us at 0, 2, so right there, this is t equals 2. T equals 3 has us at -1 and then 3, so we're over here, and this is t equals 3. And then t equals 4 would put us here, t equals 5 would put us here, t equals 6 would put us here. And you may or may not have recognized this just yet, but essentially this is going to map out a curve for us. If we were to do points in between, because we don't have to restrict ourselves to those integers, we could have done t equals 0.2 or 0.58 or whatever. We could go all the way through that. And you see we're going to get it's looking like a curve. It's not going to end up being a sawtooth. If you know, it's not going to be some straight, jagged thing like that or anything like that. It's going to be a nice curve like that as you go through the t values, and you'll actually move along it this way as you go through time t. All right, so it's more like this is the path you would follow as you went through this. This could be, I don't know, the tail of a fish as it swims, or you know, some sort of wave at the beach or something like that, something moving up like that. But basically, that's what you have there. If we go ahead and do substitution, if we substitute in, we can see here that y is equal to t. So since y equals t, we can actually substitute that in to the sine of pi t over 2. We can take that and substitute in for t, and we'll get that x equals sine of pi y over 2. And you see, there's your sine function right there. But notice this is not a function. It fails the vertical line test. But it's basically a, you know, let's put it this way. It's your arc sine function, except we're not stopping, and so we're not keeping it as a function, we're allowing it to move on. But we could, you know, invert. If you had switched the x's and y's, then it would have been horizontal, but there you go. You see it, you get a sine function, it's just a vertical sine function there. Okay, let's take a look at another example. Here, sketch the curve defined by the parametric equation x equals t squared, y equals t plus 1. So let's go ahead and try this one. And what we have, again, is our t values. Notice t can go anywhere from -infinity to +infinity. So we can have all these values and go maybe -2, -1, 0, 1, 2. Let's take a look at those. And you can keep going, so hopefully you can get the shape. X is equal to t squared, so we're going to have 4, 1, 0, 1, 4, just like that. And then continuing on. Y is equal to t plus 1. That's y equals t plus 1. And here it's going to be, you know, so on and so forth. -1, 0, 1, 2, 3. And then we can combine these together into our xy coordinates. And we're going to get a bunch of them, and we'll get 4, -1. We'll get 1, 0. We'll get 0, 1, sorry, these aren't lining up anymore. We'll get 1, 2, we'll get 4, 3, and then so on and so forth. Sorry, these kind of got a little off from me, but they line up that way. Anyway, you'll have these points. And if we go and try to start actually graphing this, we can start here, and at t equals 0, or We can even start it actually at t equals -2. We have the point 4, -1. So we'd have to come out here 1, 2, 3, 4, and then -1, and that's our first point. That's t equals -2. And then at t equals -1, we have the point 1, 0. So 1, 0 right here. This is t equals -1. And then at t equals 0, we have the point, t equals 0, we have the point 0, 1. So that puts us up here. And then at, excuse me, at, this is t equals 0. At t equals 1, we have the point 1, 2. So we're here at t equals, that's t equals 1. And then at t equals 2, we have the point 4, and then 3. So we're up here. This is t equals 2. And we could go on and so on and so forth. And what you should be noticing is that this is a sideways parabola. Again, not a function, but it's sideways. Because it's sideways like that, fails the vertical line test. But there you go. We have we're basically getting a parabola out of this, just a sideways one. And if we go through and do substitution, we can substitute in one to the other. So we have x equals t squared, and we have y equals t plus 1, which means that t equals y minus 1. And so we can substitute that in over here. We can take that and substitute it in, and we'll get x equals y minus 1 squared. And so this is basically a parabola, but as a function of y instead of a function of x. And that gives us that x is equal to y squared minus 2y plus 1. So definitely a parabola, just a sideways one. All right, so be careful about that if you're doing this. If you had solved it the other way, you made this a function of x, you would have taken the square root of t. Just as a little note, you would have said that t equals plus or minus the square root of x, and then you would have had to have dealt with that way. That would have given us the top half and the bottom half, which is what happens when you try to solve this one anyway. So let's go ahead on to the next example, example 3. We're given a parametric equations and parameter interval for the motion of a particle in the xy plane. Identify the particle's path by finding a Cartesian equation for it. Graph the Cartesian equation, indicate the portion of the graphs traced by the particle and the motion. So when I look at this here, what I'm basically wanting to do is say, all right, well, first I want to think, what kind of motion am I going to see here? Well, in the x direction, we're moving according to cosine. In the y direction, we're moving according to sine. And hopefully that's familiar to you, and we're going from 0 to 2 pi. And if it's not super familiar to you, then you need to go back and think about your unit circle some more. Because if you start doing points on this, what happens is you get t, or cosine of t, or sine of t. You plug in 0, cosine of 0 is 1, this is 0. Skip to pi over 2, you get 0, you get 1, you could do 5 pi over 4s, you could do all these values, and what you're going to ultimately map out with this is the unit circle. This is going to take us around the unit circle. So as we start here at t equals 0, and we're going to move around this way to t equals, this is t equals 0, and as we progress around the values of t, we're going to keep moving around this, and this particle is basically going to go around a circle one time from 0 to 2 pi and end up right back where it started. All right, and you could even think of this as the Pythagorean identity, which is the idea that cosine squared t plus sine squared t equals 1, which is also x squared, because cosine squared, right? X squared equals cosine squared t. X squared plus, and then y squared equals sine squared of t. So x squared plus y squared equals 1. And again, that's our equation for a circle with a radius of 1 right there. Okay? So even just looking at it, we should have been able to kind of intuit that that's what we should get here. So let's take a look at this next one. If we look at this next one, we should immediately see that we're not just getting x equals cosine, we're getting x equals 2 cosine. So if we start plugging in values, we're going to end up with, starting out at 2 instead of at 1. So if we do our table here, right, where these are our t values, like we start with 0, we start with pi over 2, stuff like that. For our cosine, it's 2 cosine of t. We plug in 0, we get 1. We multiply it by 2, we get a 2. We plug in pi over 2, right? We get 0, and 2 times 0, it's still 0. For the negative 2 sine of t, if we plug in 0, we get 0. And if we plug in pi over 2, we get a 1, and we end up with a negative 2 there. Okay? So what we should expect from this one is to have a circle with a radius of 2 now, because we're starting out at 2 here, and we're going out to negative 2 over here. Oops, why did I put my circle so far down? We're going out to negative 2 on this direction, and we should end up, just from looking at this one, going around a circle of radius 2 here. And but this time, notice that we're going down in the y direction. This is headed down, and not just x is decreasing, this is going down. So we're actually going to go this way. We started here, this was t equals 0, and this is t equals pi over 2. So after pi over 2 amount of time, we should have curved back around here. If we had done pi over 4, we would have ended up here, and pi over 6 here, and pi over 3 here, and so on and so forth. And we're going to keep going around. And notice again, we're going all the way to 2 pi. And if we plug in 2 pi, it should take us back around all the way to the start here, because if we plug in 2 pi, what do we get? Cosine of 2 pi is 1, so we get a 2 again, and the sine of 2 pi is 0, so we end up with a 0 again. So it takes us right back around to where we started. Now how do we turn this into a function? Well, we start solving for it. Here we can say x over 2 equals cosine of t, and y over, or negative y over 2 is equal to sine of t. And again, cosine squared of t plus sine squared of t is equal to 1. And so then we can square both of those. So this will be x squared over 4 plus y squared over 4 equals 1. And then this gives us, we multiply everything by 4, we get x squared plus y squared equals 4. And that's the equation for, well, x squared plus y squared equals 2 squared. Sorry, dog's barking now. And so we have x squared plus y squared equals 2 squared, which is x squared plus y squared equals the radius r, which is 2 then. And we get back what we had. So next, let's take a look at example 4 here. I think I'm actually going to leave this one for you to try, especially after you've watched and tried the stuff from my first video. But I'm going to leave you for this one. Just note here that we're doing t greater than or equal to 0. We're starting at 0. And I'll write it out for you in the notes for you to see. And then coming along here, we're doing the last example here, I think this is the last example, yep. The graph of any function y equals f of x can always be given a natural parameterization, because again, we can have any number of them we want, and this is going to just be the simplest thing you can do, which is just make x equal to t. All right, we're going to call that our natural parameterization, and y then is equal to some function of t. And then you're just going to move steadily along an x and let y go along there. And it says the domain of the parameter in this case is the same as the domain of the function. All right, so the position p of xy of a particle moving in the xy plane is given by the equation's parameter intervals. X equals t, y equals a function of t, which is t squared, and we are ranging from negative t, or t from negative infinity to positive infinity. So identify the path the particle is traced. And so this is the easiest kind that you can do, because we can simply just substitute that, oops, I drew there in the wrong place, we can simply just substitute that in right there, and we will get, y equals x squared. And so we all know that graph. That's just simply a it's just simply a parabola like that, which again, try not to do it quite so simply if you're doing my challenge from this first video, but you can just do it like that and get it kind of simple, but see if you can come up with some other parameterizations for it as well. Just challenges to you to get you really thinking along these lines and see if you really know it. Except here in this case, we're moving from negative infinity on t, and we're moving along this way as t moves along. So we started like, say we started our stopwatch here, this is t equals 0. This, you could think of this as like everything that happened before we started timing it and reset our stopwatch. And then after that, it moves on like that. Okay, so there's time before you started your stopwatch, and there's time, so there's time before you started your stopwatch, and there's time afterwards, if you want to think about why we have negative times like that. So, all right, that's pretty much it for this, and hopefully it makes some kind of sense.